Flight has become ever present in our daily lives. Every year, nearly 3 billion passengers board commercial flights around the world, bound for everything from exotic vacations to quick business trips. But even if you personally don't fly very often, you still depend on aircraft to bring in cargo that eventually ends up on the shelves of our stores and markets. When you combine cargo flights and commercial passenger flights here in the U.S. alone, that equates to more than 10 million flights that take off and land safely every year. When you look at worldwide flights, that number goes up by millions more. With this commendable record, it would be easy for aircraft manufacturers to rely on the status quo and continue to build the same types of safe, efficient, and dependable aircraft for the foreseeable future. But the status quo just won't do. Changes in technology, materials, and scores of other areas continue to unfold that will make future aircraft better in virtually every way. These changes won't come easy, though. Researchers in both the airline industry and government spend years looking over new designs and ideas to make sure that they will work perfectly. This collaboration between industry and government is important because government researchers can help mature new ideas that will eventually be picked up by its industry partners. But if aircraft are already this good, what areas need to mature to make them even better? Today on NASA X, we will see how industry and NASA are working together to make aircraft quieter, greener, and more fuel efficient. We will follow members of NASA's Environmentally Responsible Aviation Project as they work with industry engineers to develop the aircraft of the future that are substantially different in form and function from the aircraft that we fly on today. If you were to book a flight today and there were multiple options for airlines to go to your desired spot, generally what would be the key decision point for booking that particular flight? For many of us, the deciding point would be cost. There are certainly other factors that would go into that decision, but more often, cost wins out over other concerns. Clearly, the airline industry is a business, so keeping costs down to lure more passengers is a huge driver. Airlines are very good at understanding the economics of flight, but one of the biggest fluctuating costs comes from gas prices. If gas prices go up, then generally ticket prices rise as well. One clear way for airlines to combat big fuel bills is to fly aircraft that are more efficient and use less fuel. And theoretically, ticket prices should go down as well. This push and pull has been going on for years. Though it may not seem like it, flying today is dramatically less expensive than it was even a few decades ago. Adjusted for inflation, a ticket today will cost on average about 40% less than a ticket would have in the 1950s. There are many reasons for this change, but one in particular is that aircraft of today are significantly more efficient than those of the recent past and are continuing to improve every year. With that efficiency, there are added benefits as well, like reduction in air pollution and noise pollution, and even an increase in safety. To help keep this trend moving forward, NASA made steps in 2009 to continue its place as the world leader in the study of efficient aircraft. They implemented a project called the Environmentally Responsible Aviation Project in a bid to explore aircraft concepts and technologies that will continue to reduce the impact of aviation on the environment over the next 30 years. During the first 3-year phase, engineers assessed dozens of areas of environmentally friendly aircraft technologies. With these assessments in hand, they then took some of the most promising technologies and began looking at how they would react in a real-world environment. Some of those experiments included non-stick coatings for low-drag wing designs, laboratory testing of a new composite manufacturing technique, advanced engine testing, and test flights of a remotely piloted hybrid wing body prototype. After the first 3 years of testing, the verdict was in. The ideas that were studied proved to be incredibly successful in making very quiet aircraft with low carbon footprints. The ERA project engineers have taken the valuable lessons learned from Phase 1 and are now beginning to integrate these ideas together to make an even larger improvement in the next phase of testing. In Phase 2, NASA has chosen 8 large-scale integrated technology demonstrations to advance ERA research. The demonstrations are designed to further the project's goals of simultaneous reduction in the amount of fuel used, the level of noise, and the emissions produced by tomorrow's aircraft. Researchers will focus on 5 areas: aircraft drag reduction through innovative flow control concepts, weight reduction for composite aircraft structures, fuel and noise reduction from advanced engines, emissions reductions from improved engine combustors, and fuel consumption and community noise reduction through innovative airframe and engine integration designs.
ERA from the beginning in 2010 had some very aggressive goals relative to fuel burn, a 50% reduction in fuel burn, noise, 42 decibels less than stage 4 noise, and for emissions, 70% less than the Cape 6 emission standards, which are international standards. So lofty goals that they've been working at. And during the first phase, they did a lot of exploratory investigations that could look at all of these technologies working together to see what the probability of outcome would be. So out of that first 3 years' work, they came up with 8 investment strategies, integrated test demonstrations to invest in. And these aren't aircraft dependent necessarily. So they could work on something like what we're doing now, doing risk reduction work for a test that will be looking at a blended wing body configuration, a fairly advanced configuration. But many of these technologies will work on current configurations that we see flying right now. Across the street in the National Full-Scale Aeronautics Facility, we've got a test that would be flown on a 757 Eco demonstrator.
As Dr. Waggoner mentioned, testing active flow control has been completed on the vertical tail section of a 757 here in the National Full-Scale Aerodynamics Complex, or NFAC. The NFAC is the second largest wind tunnel in the world and is uniquely qualified to test full-scale configurations like this. This vertical tail section was taken off of a Boeing 757 and fitted with active flow control jets before it was brought into this facility. Now that it's here, researchers can begin the hard work of understanding if this unique technology is viable on aircraft. To understand what is being tested, let's first look at how the tail section of an aircraft works. Here is Boeing's Ed Whalen to explain.
So the vertical tail on a commercial aircraft serves several purposes. The purpose that we're focused on here is dealing with the situation when there's an engine failure on the aircraft. It turns out that the vertical tail is sized largely because of this engine failure condition. And so when the engine fails in like a twin engine airplane, there's a large thrust asymmetry because one engine will be at high thrust and the other engine will be at 0. And the rudder and the vertical tail is there to straighten the airplane out in that situation. So take out that asymmetric thrust, the moment that that asymmetric thrust creates, and allow the airplane to fly straight and land straight on the runway. Most of the time the airplane is carrying around this vertical tail that is really sized just for this one situation where the engine fails. It's a very improbable circumstance for commercial aircraft. So all that time that you have that vertical tail, it's sort of a penalty that the airplane pays to carry this around in the case that this emergency happens. So the idea is that if we can add the active flow control in, we can reduce the size of the vertical tail. And so we're not sort of carrying around that extra penalty of this bigger tail. We're carrying around the right size tail for the normal aircraft operation, and we're turning on the active flow control in an emergency situation or in another situation where high vertical tail or rudder authority is required.
As Ed mentioned, commercial aircraft are designed with a large vertical tail and rudder for maneuverability and an emergency engine out scenario. Because engine stalls are such an infrequent occurrence, the weight of such a large rudder makes the aircraft less efficient. The basic principles of flight include lift, drag, thrust, and weight. In order for an airplane to fly, thrust has to equal drag, and lift has to equal weight. So if you can reduce unintentional drag, then you can make your aircraft more efficient. But the plane still has to operate with an emergency engine out procedure. Smooth air must flow over an aircraft's surface for it to perform optimally. Researchers have added active flow control sweeping jets to ensure that sufficient air is flowing over aircraft surfaces.
What the active flow control tries to do is it adds energy to the flow, in this case through the sweeping jet actuator, and when it does that, it reduces the separation on the rudder. So when the rudder is at a high deflection angle, like 30 degrees, it starts to experience some flow separation, and that reduces its ability to create aerodynamic force. So what we do is we add these jets in the right place with the right spacing and the right mass flow levels and things like that, and that reduces the separation on the rudder and allows the tail to provide its sort of maximum potential aerodynamic force.
So what we're using here to generate this effect on the aerodynamics around the tail is something that we call sweeping jet actuators. And the way they work is air comes in, pressurized air comes in, and then it flows through. And there's a feedback channel here that makes the jet oscillate as it comes out of the nozzle. And on the model here, you can see that these jets are positioned along the rudder hinge line. And so the air comes through there and flows and makes the effect that we're looking for to cause the change in side force. The string that you see taped on the rudder here helps to tell what direction the air is moving as it moves over that surface. Since we can't see the air itself, this is a way to visualize what's going on. And as we turn on the actuators, you'll see these change direction. And near the actuators, they'll oscillate because the actuator itself is oscillating, but also because the flow coming downstream is separated until we turn actuators on, and then it changes the patterns that you see. Investment needs to be made now to be able to realize these benefits in the future. And so ERA is set up to really look at ways to help protect the environment. And so the technologies we're working on in this specific instance will end up causing less drag on aircraft, which results in less fuel burned. And so that's obviously a benefit in terms of emissions as well as just an overall economic benefit for the airlines.
After the analysis was completed, the wind tunnel tests conclusively showed that the goal of a 20% increase in side force was achieved with the active flow control jets. Research will soon begin to focus on validating these results on actual flight tests in the near future.
If you think about it, that's been a full-scale hardware-in-the-loop simulation we've just done. We'll take that hardware and actually apply it to a 757 that's been leased for the purposes of this experiment, and we'll go off and fly it and see if the performance we can demonstrate in flight essentially is consistent with what we measured in the 40x80 at NASA Ames. We're confident it will be, and we're looking forward to the experiment.
So we've seen how testing is performed on full-scale aircraft parts, but researchers also test small-scale and computer models as well to better understand how to improve aircraft performance. Here at the 11-foot tunnel at NASA Ames, researchers are looking at turbo propulsion simulators, or TPS units. The hope is that these tests will help better understand how moving engine configurations may fundamentally change aircraft design, while also making it more efficient. Here is NASA's Kevin James to explain.
One of the big problems with the next generation of airplanes is how do you actually integrate the propulsion system with the aircraft? We call that PAI, or propulsion airframe integration. The problem is the engines have gotten to be so big, which is why they're really efficient, and it's also why they're quiet, is actually their size. Their size is approaching sort of the tube diameter of the airplanes that they fly on. If you look at a 737 and you look at the size of the engines that are hanging underneath the wing, they're approaching the size of the fuselage that we ride in. So a big problem is how do you take these engines and integrate them with the airframe itself? How do you get the airplane to fly as a cohesive unit? One of the problems that we're looking at on our particular propulsion airframe integration problem is that we're looking at an entirely new aircraft concept, and the engines are actually going on the upper surface of the wing. That does a variety of things. If you look at an existing aircraft, the engine diameters have gotten to be so big, the only way we can make them bigger is we actually shove them up into the wing, which causes real problems with how the wing works, or we put longer landing gear on the airplane. Well, if you look at the trade-offs, the cost of carrying the weight of that longer landing gear around for the life of the airplane doesn't actually pay for putting the bigger engines on it. So putting bigger engines underneath the wings is a real problem, especially for smaller aircraft. So now we're working on putting the engines on the upper surface. The problem is it's the upper surface of the wing that actually does the work that produces the lift that allows you to fly. So if you aren't very clever about how you integrate the engines on the upper surface of the aircraft, you totally destroy its ability to fly efficiently.
Understanding this issue, NASA researchers have been testing hybrid wing-body aircraft that could revolutionize flight. In addition to flying models in the desert, researchers are also putting these TPS units to work in wind tunnels to better understand how new engine configurations will work with these innovative designs.
Well, this looks like a little jet engine, and that's actually kind of what it is. It's actually a jet engine, a small jet engine that runs on high-pressure air instead of kerosene or Jet A. And we do this because it's actually a problem to burn kerosene in the wind tunnel environment. It makes a mess. So we use these to simulate jet engines on real aircraft. These turbo propulsion simulators, or TPS units, are being set up and developed for testing on a hybrid wing body or a blended wing body platform that's part of the ERA program. There will be two of them, and they are mounted on the upper surface of the aircraft towards the aft between the tails. These units will actually simulate the way a real jet engine would perform on the real aircraft, but we're doing it all at model scale, and we're doing it in a wind tunnel environment where we can measure the forces and the moments and the off-body flow fields.
Part of this research is also helping engineers better understand what future aircraft will look like.
I'd say the future's wide open. There's a lot of good places to put engines. There's a lot of good ways to design airplanes. If your goal is to improve your fuel economy and you reduce emissions, there's a variety of ways that we can go after it. Some of it is going to be looking at advances in the propulsion, trying to improve the efficiency of the combustors, trying to change the emission characteristics of our engines. Like I said, there's some low-hanging fruit in how do you actually integrate that engine with the airframe. And it turns out that if you're really clever about this and you do a good job, you can produce an airplane that's more efficient with the engine cleanly integrated with the aircraft than the aircraft without the engine at all. The hope is that if you present the American people with airplanes that don't look like airplanes, that they're not necessarily a tube and a wing, or they're not necessarily maybe even a conventional looking jet engine. These are still perfectly valid airplanes, and they actually may be better airplanes than what we have today, that they're going to allow you to travel farther and faster and cheaper with fewer emissions and like I said, cheaper tickets. I think the way airplanes look are going to change for sure in the next 25 years, and I hope that people just are willing to accept that these changes are progress.
As we have seen so far, there are some unique and cutting-edge ideas on the drawing board for making aircraft more efficient. Irrespective of whether you are flying today or 30 years from now, aircraft will always have to contend with external issues like weather and other environmental factors in the goal to become more efficient. What may come as a surprise is how seemingly innocuous items like dirt and even bugs can cause an aircraft to become less efficient. To understand this, let's think back about the four forces of flight. When air passes over the aircraft wing, the aircraft will rise. The goal is to have what engineers call laminar flow over the wings. Laminar flow is when air passes over the wings evenly, without any turbulence. When areas of the aircraft's leading edges do not allow air to pass over them smoothly, it causes more drag and turbulence, which in turn makes the aircraft less efficient and forces it to burn more fuel. Believe it or not, even the smallest of bugs hitting a wing can cause the aircraft to become less efficient. Researchers here at NASA Langley are attempting to solve this problem by testing new aircraft coating that won't minimize bug strikes but will prevent the bug residue from sticking to the aircraft surface.
What we're doing here is we're developing some engineered surfaces to prevent bugs from sticking to aircraft wings. And this work is actually part of a project called the Environmentally Responsible Aviation. And The objective of this is to prevent bugs from sticking so that we can enhance or maintain laminar flow over aircraft wings. What that means is that we're preventing turbulent flow so that you have more efficient aerodynamics. What we're doing now is testing it in a more realistic environment where we're simulating takeoff and landing conditions. That's why we want it in the wind tunnel. And we actually designed a gun so we could shoot bugs at it and see how effective the coatings are.
The testing is being performed in the small wind tunnel at NASA Langley Research Center. Researchers place test samples of the different materials over the wing model. When the system is ready, they fire live fruit flies at the model to see if the bugs stick or not.
If you compare what you see there versus here, those numbers are marking the bug hits, and you can barely see it. So that's the objective. What we're trying to do is prevent the residues that are sticking up from tripping the laminar flow. So you have laminar flow instead of turbulent flow. When that happens, especially during cruise when you're flying long distances, because the aerodynamics are more efficient, then you actually burn less fuel. We started looking at commercial coatings just to make sure we're not missing any of what's already effective out there. And between the commercial coatings we've looked at and new coatings and surfaces that we've engineered and modified, we've looked at about 60 different surfaces. The hope is that we can get the most effective surfaces down selected and develop further for application. And from that set, we're looking at perhaps down selecting to about 3 that we could investigate further.
Research continues on this project, and so far the results seem very promising. NASA is not settling for the status quo and is in fact pushing forward in many new directions, from seemingly innocuous bug strikes all the way to full-scale testing on aircraft. The researchers of the Environmentally Responsible Aviation Team are leaving no stone unturned in an effort to push the boundaries and find ways to make aircraft of today and those of tomorrow as efficient as possible.
The world has changed significantly in the last 100 years. Just think, we went from just 1 horsepower back then to tens of millions of horsepower today. So what do you think the next 100 years will bring? I can't tell for sure, but I do know one thing. NASA will be there helping to lead the way. To find out how, follow me and the NASA X team as we explore the world of NASA to see what technologies are being discovered by the brilliant men and women who work there. Each exciting episode will go behind the gates of NASA, letting you see the technologies of the future today. So, like us on Facebook and follow us on Twitter right now to begin your exploration with NASA X today.